Welcome to Summarize Science, where we break down the big ideas from the frontiers of research. Today, we're looking at a fascinating paper that tackles two of the biggest puzzles in physics: the mysterious nature of dark matter and the surprisingly tiny mass of neutrinos. What if a single, elegant theory could explain both and even offer a way to prove it? The researchers start with a popular model for explaining neutrino masses called the type I seesaw mechanism. They point out that this model has a leftover symmetry, which they call lepton parity. By cleverly extending the model with a couple of new particles, this symmetry can be used to define darkness, effectively separating a dark sector from our normal world. One of these new particles is forced by this symmetry to be perfectly stable, making it a natural and compelling candidate for dark matter. It's a neat idea, but the real excitement comes from how we could actually test it. The theory predicts two distinct, observable signatures that could show up in future experiments, depending on how a new scalar particle, named sigma, interacts with the famous Higgs boson. In the first scenario, if the interaction between sigma and the Higgs is strong, it would have triggered a very special event in the infant universe. This event is called a strong first-order electroweak phase transition, which is a fancy way of saying the universe underwent a violent, boiling-like change. Imagine bubbles of the new state of the universe forming, expanding, and smashing into each other at incredible speeds. These cosmic collisions would have been powerful enough to create ripples in the very fabric of spacetime, a background of gravitational waves. This plot here is the money shot. It shows the predicted sound spectrum of those ancient waves. You can see the predicted signals, labeled BP1, 2, and 3, fall squarely within the detection range of future experiments like DESIGO and LISA. Finding these specific ripples would be like hearing an echo from the universe's very first second, providing smoking gun evidence for this model. But what if that interaction was weak? This leads to a completely different, but equally detectable, clue. In this case, the sigma particle would have survived for a much longer time in the early universe, before finally decaying. Its decay would release a burst of extra light, relativistic particles, essentially adding a bit of extra glow to the young cosmos. This extra radiation is something we can hunt for by studying the cosmic microwave background, the oldest light in the universe. Scientists look for this signature as a deviation called delta N_EFF, or the effective number of neutrino species. This graph shows that the theory predicts specific values for this deviation, which are just beyond our current ability to measure. However, next-generation CMB experiments are being designed to reach exactly this level of sensitivity. This gives astronomers a second, completely independent way to check if this theory is correct. So, to recap the essential points, this research presents a unified framework where the explanation for neutrino masses naturally provides a candidate for dark matter. The most exciting part is that this isn't just theoretical mathematics, it makes concrete, testable predictions. For the future, this means we have a clear roadmap for what to look for. The hunt is on for either a faint hum of gravitational waves from a cosmic boiling event, or a subtle extra glow in the baby picture of our universe. Finding either one wouldn't just solve the problem of dark matter, it would revolutionize our understanding of the universe's first moments.